About phase diagrams, and what we say about phase diagram is a very useful because you can extract you can extract many important information from the phase diagrams. So one of those information اللي هو, so you can know at a certain composition, at a certain temperature, how many phases exist, right? So for example, if you have a certain composition, a certain temperature, you will know whether you have a single phase, more than one phase, whether they are liquid or they're solid, right? And in order to introduce you to the phase diagram, we said last time, we're going to start with a very simple system, right? And we started with a system that's called isomorphous binary phase diagram. And we call it isomorphous because the two components that are making up this phase diagram, they can completely dissolve in each other to form a single solid solution. And in the liquid phase also, they can completely dissolve in each other to form a single liquid solution. So we call it isomorphous, and then binary because you have two components. They're making the system اللي هو copper and nickel, تمام? So we'll start with this simple system اللي هو copper and nickel. And we notice that regardless of how much nickel you add to the copper, at the end, both of them, they can completely dissolve in each other. Okay, and today I'm going to introduce you to a little bit more complicated phase diagrams. In many cases, when you want to mix two metals to form solid solution, the problem is they cannot completely dissolve in each other. There is solubility limit. And that was the main message from this slide. If you remember, we say that for some, if you add more sugar to water, there is something called solubility limit. If you pass the solubility limit, then you're going to have two phases instead of one phase over here. And we call this one solubility limit. Similarly, when you want to make solid solution that is composed of more than one solid, you're using more than one element to form that alloy, there's a solubility limit. So material A can accommodate some of B up to a certain point, but then after that point, you're going to have two solid phases instead of having a single solid phase that can have both of these two components, okay? So most of the metals, when you try to form a solid solution, because there is a solubility limit, you end up having more than one solid phase, right? So in this example, what was special about the copper and nickel is they can form a single solid phase. Today, we're going to move to another system. I'm going to introduce you to another system. It's called binary eutectic systems, right? In this system, there is some limitation on how much each solid phase can accommodate one of the elements. Okay, let me walk you through this diagram over here. So as you can see in this diagram, you have, this is for copper and silver system. Okay, so you have copper and you're adding to it silver. Now there's something different here because copper and nickel, they can completely dissolve in each other. Now when you have copper and silver, you have different case because there will be some solubility limit, as I mentioned earlier. Okay, so again, this is a phase diagram. In the y-axis, you have the temperature. In the x-axis, you have the composition. You know? Now, if you have 0% silver, I mean you have 100% copper. Okay, you have a pure copper. Okay, you notice that at this temperature, it's a solid phase, right? Once you hit 1000, maybe 100, you're gonna melt the solids and you're gonna form liquid phase. If you go to the 100% silver, 0 copper, right? So what's gonna happen is the melting temperature will gonna be around 900 Celsius. Now, you notice that there are two regions here. One is called alpha, one is called beta. So alpha is representing a pure here is representing a pure phase of, oh sorry, it's representing a rich phase of copper, because at copper, when you have 0% silver, you have 100% copper. And the phase that exists is alpha, right? So we have alpha phase, and this alpha phase can accommodate, if you start to add some silver, if you start to add some silver to it, it still have alpha phase, right? If you add more silver, it still has alpha phase. You have a single solid solution. So at this point, at this composition, you have alpha phase that has two components. It has silver and copper, but it's rich of copper. It has more copper than silver, right? Until you have this line over here. You see the line over here? It's called solvus line. Once you have this line and you add more silver, alpha cannot accommodate more of this silver, right? So I mean, you're gonna start to have another phase. Another phase we call it beta. So now, in addition to have for alpha, now you have beta. Okay. Similar, if you go to the other side, you start with 100% silver. If you're at this point, you have pure silver. Now, if you start to add copper to it, what's going to happen? If you start to add copper to it, the beta can accommodate some of the copper, until you hit the solvus line, right? So once you hit the solvus line, you reach the solubility limit. That means if the more copper you add, now you're going to form another solid phase اللي هي alpha. So at the end of the day, there is a solubility limit that's represented by what's called solvus line. How the solvus line? From this point up to here, this is called solvus line. Right? This is representing the maximum solubility or the solubility limit of a solid phase for certain elements. Okay, wonderful. So in this diagram, this phase diagram is called eutectic. And why it's called eutectic? Because you can notice clearly that if you are at this point here, okay, at this point, let's say 48%, you are at this point. At this point, how many phases exist? One phase, the whole liquid. What is the composition of that phase? The composition is 48% silver, 60% copper. Now, once you start to cool down, okay, you come to this region. Now you have two phases, the liquid plus alpha. Part of the liquid will transform to alpha, and part of it going to stay as it is. If you keep cooling down below this temperature, 779, if you cool below this temperature, you come to this point. Now all the remaining liquid gonna transform to alpha plus beta. Hello? Now don't forget that part of the liquid already transformed to a special type of alpha. We're gonna talk about, we call this one primary alpha. And once you go below this temperature, the remaining liquid gonna transform to alpha plus beta. معناته هنا الالفا بلس بيتا اللي هنا alpha, this alpha, it's two types of alpha, right? في اللي هو البرايمري alpha وفي اللي that's formed after you pass this eutectic temperature. Again, so below the eutectic temperature, that is called eutectic temperature, TE, below the eutectic temperature, all the remaining liquid, any liquid that you have, is going to transform to alpha plus beta. Now, at this point, at this composition, we say that if you cool down from the top, from the liquid up to this point, part of the liquid already transformed to alpha. So at this point, now we have two types of alpha. Alpha that's formed before the eutectic temperature اللي هي we call it primary alpha, and the new alpha also that's formed as a result of the liquid transformation, because always liquid, when you go below this temperature, you're going to transform to special type of alpha plus of beta. تمام? We're going to talk about this also today in today's lecture, inshallah, at the end of today's lecture. طيب. So the point here is, at this composition, 48%, liquid, when you cool down, it has to go through a region where you have part of the liquid gonna solidify to alpha, and then if you go to this point, all the liquid can transform to solid phase. Similarly, if you are at this point, let's say if you are at 80 weight percent, you have liquid. If you cool down in this region, you have liquid plus beta, and then here you get all the liquid transformed to solid. طيب. Similarly, if you have a solid phase at 40 weight percent, at 48 weight percent, at this point, 600 Celsius, 40 weight percent, you have alpha plus beta. If you start to heat up, you heat up. Once you hit this line, طيب, the solid gonna partially melt. So you're gonna have alpha plus liquid, right? If you keep heating up, you're gonna completely melt the solid solution that you have. Similarly here, if you have 80 weight percent, you have alpha plus beta. If you are heating up, the solid is gonna partially melt before it's completely melt. So in this region and in this region, you have to go through a transition region, before the solids completely melt, right? Or before the liquid completely solidify. You have to go through these regions. هذا region وهذا region. However, there is a special point in this diagram. هذا البوينت اللي هي this composition اللي هو يسموه eutectic composition. طيب. You can directly go from solid phase. You're gonna go from solid phase directly to liquid phase without passing through this transition region. Similarly, if you are at this point and you want to solidify the liquid can directly go to forming two solid phase, alpha plus beta, without the need of forming primary alpha or primary beta. واضح? This is why we call this one. We call this point a eutectic point. اللي يكون عندها eutectic reaction, is invariant point. فيها eutectic reaction اللي يكون at a specific composition is called eutectic composition, and specific temperature is called eutectic temperature. So at this, so if you are anywhere, if you go below, anywhere between 8% and 91.2%, and you go below this temperature, اللي هو eutectic temperature, any liquid you have, it's gonna transform to a special type of alpha plus beta, تمام? Alpha plus beta. But if you are in this region or in this region, in addition to this special type of alpha and beta, you're gonna have a primary alpha. It's called primary alpha, and you're gonna get primary beta. Hello. So again, if you are between these two compositions, who are 88% and 91%, right? If you are in this region, and if you cool down below the eutectic temperature, any liquid you have is going to transform to a special type of alpha plus beta. طيب. But in addition to that, if you are a composition below 71, هنا, you're going to have, in addition to alpha plus beta, you're going to get a primary alpha. If you have a composition more than 71.1, here at this point, you're gonna, in addition to alpha plus beta, you're gonna get primary beta. Okay, so that means only at this point, only at this composition, that liquid, all the liquid that you have, gonna transform to directly to alpha plus beta without primary alpha, without primary beta. واضح شباب؟ Okay, we call this one eutectic reaction. Eutectic reaction عندك liquid gonna transform to alpha plus beta. Okay, and also the liquid at 71.9 اللي هي at this point gonna transform to alpha beta. So at this point, تمام, the composition you have, so the liquid can transform to alpha plus beta. The composition, so now at this point you have two phases, alpha beta. The composition of alpha is you're gonna construct the horizontal line, the tie line, until you hit this point and you hit this point. Right? So the composition of alpha and beta is, so the composition of alpha, you're gonna have this horizontal line, and then you go down. This be around 8%. The composition of beta, you're gonna go here and then you head down. It's gonna be around 91.2%. So why this is called eutectic? Because eutectic is a Greek word that means the solid can easily melt. And you can understand now why we call it eutectic, because here the liquid can easily melt, the two phases, alpha plus beta, can easily melt directly to liquid. However, if you have a different composition, if you have this, in this range of composition between 8 and 71.9, or in this region, the solid first gonna melt it, partially melt, and then you need to apply higher temperature in order to completely melt the solid. Similarly here, right? So part of the solid will melt, and then you need to apply higher temperature before you can completely melt the solid. So there is a special point in this phase diagram where the solid can completely and quickly melt it, right? So in some application, if you want to make an alloy of two components, you need to know what is this point where you can apply smaller you can apply lower temperature and small amount of energy in order to completely melt the material. And you can agree with me, this is very important, that we have seen this in many applications around this. And one of the famous example is the soldering material, right? So maybe we have done with electronic circuits before. We're going to use this, a gun that's going to provide heat, right? And then you have the solder material, and then once you apply the heat to solder material, what's going to happen is it's going to melt, and then it's going to solidify very quickly. So it's going to melt very quick, and then it's going to solidify very quick, right? So that soldering material actually is made of lead and tin. And this is the phase diagram of lead and tin. So this is the phase diagram of lead and tin. So most of the soldering material you're going to find in the market, actually it has a special composition. It has around 61.9 tin, and the remaining is lead. Why most of the soldering material has this composition? Because the manufacturer would like the customer to have easy time to melt the soldering material, and also to have that soldering material to solidify in a quick way. Again, in the phase diagram, we can know how many phases exist, and also we can know what is the weight fraction of each phase. So imagine you have this composition, 40 weight percent tin, and you are at 150 Celsius at this point. So how many phases exist? So at this point, you have two main phases, alpha plus beta. Okay, what is the total alpha? What is the total beta? Why I'm saying total alpha? Because we know that we have more than one alpha. We have two types of alpha. Okay, but for the time being, the question is how much alpha you have, total alpha and beta. Okay, so the way that we can know. Before that, first we say how many phases exist. We said we have two phases, alpha plus beta. Then we say, what is the composition of each phase? The composition, we're going to construct this tie line over here, right? So this tie line, and the distance, we call this distance R, this distance S, right? So in order to know the composition, we're going to construct the tie line, and then we're going to head down to the x-axis to know what is the composition of alpha. So it's 11 weight percent. The composition of beta is 99 weight percent. This is not a weird information, because we already know that alpha is rich of 10. Sorry, is rich of lead, and beta is a solid phase that is rich of 10. So we're expecting that at this point, we have two phases. We expect that beta going to have most of the beta actually is 10, and we can confirm this by going to this and hitting to the going through this line and hitting the beta phase, and then when you go down to the x-axis and read the composition, around 99% of the beta actually is 10. Okay, so the first question is how many phases exist, and then what is the composition of each phase, and then the third point is what is the weight fraction of each phase. So what is the weight fraction of each phase? In order to do that, we're going to use the lever rule again. So R and S, the distance from here to here is R, and from here to here is S. So if you want to know the weight fraction of alpha, we're going to say, so with the weight fraction of alpha, we're going to take the opposite side, the distance of between the composition and the other side, which is S. We're going to say S over the total distance R plus S. Similarly, when I know the weight fraction of beta, we're going to say that it is, if you want to know the weight fraction of beta, we're going to take the opposite side, R, so R over the total distance R plus S. Okay. Okay. And if you are at weight fraction of 48%, so this is the weight fraction, 48 weight percent, and at 220 Celsius. So what you can see that you have two phases over here, right? So you have liquid plus alpha. And again, the question is, what is the composition of liquid? What is the composition of alpha? So you're going to construct this. Horizontal line over here, and then you're going to drop down to the x-axis. Yeah, so you're going to find that the alpha has 17 weight percent 10, and the liquid phase has around 46 weight percent 10. Okay, wonderful. So then we move to the third question: is what is the weight fraction of each phase? Again, so we're going to say the distance here is R and S. If you want to know the weight fraction of alpha, so alpha, we're going to say, we're going to take the distance of the opposite side, S over R plus S. Similarly, want to know the weight fraction of liquid, we're going to say it is the weight fraction of liquid, we're going to say it's the opposite sides, distance between the opposite side phase and the weight, our composition, R. So then we say R over R plus S. By doing so, we can find the weight fraction. Maybe actually you don't need to do this step. Okay, you don't need to do this step. Why? Because we know that the total fraction, if you have two phases, the total fraction has to be, if you have two phases or 3 phases or 10 phases, the total fraction has to equal to 1, right? So in this case, we have two phases. If we can find the first one, which is 0.21, then we can say it's the other phase, the weight fraction حق the other phase عبارة عن 1 minus the weight fraction of the other phase. تمام؟ So 1 minus 0.21 حيعطينا تقريبا 0.79. Okay. So I know this this is not complicated, but maybe because it's new for you, it needs some time for me to practice it. Maybe you can solve the examples in the book, and also if you have any question during the office hour, you're more than welcome. Now we want to know what's happening in terms of the microstructure as you cool down or you heat up in this phase diagram. Because remember, I have mentioned a couple of times that liquid going to transform here directly to alpha plus beta. But if you are at the composition between this point and this point, part of the liquid already transformed to alpha. We have now, at this point, you have two different types of alpha. You have alpha this alpha that's transformed from the liquid, and alpha that came from the previous stage اللي هنا فوق, on top of the eutectic temperature. طيب, we're going to talk about this in the coming few slides, inshallah. Okay, now let's start with a very simple case. If imagine you have a composition below 2% and you are at temperature around 350 Celsius, you have a liquid phase, right? If you start to cool down, you hit this region that has liquid and alpha, so part of the liquid is gonna solidify to form alpha phase, and once you hit this region, all the remaining liquid gonna transform to alpha. Now, this is only one type of alpha. This is only one type of alpha. Okay, is not the special type of alpha. It's one type of alpha. Why? Because you say that the liquid gonna transform to special type of alpha plus beta only between these two compositions. اللي هي 8 واللي هنا. Let me show you this numbers here. Sorry, 18.3 and 97.8. Only between these two compositions, if you cool below the eutectic temperature, the liquid can transform to a special type of alpha plus beta. Hello? In addition to whatever already have been formed before. Okay, so because here you are below this composition, so all the liquid can transform at the end to a single type of alpha. Okay, if you keep cooling down up to room temperature, nothing gonna happen. You still have a single phase of solid phase, of alpha phase. Now, what's gonna happen if you have higher composition? You have more 10. Okay, here you start with liquid phase. You cool down, you hit this region. Part of the liquid gonna start to nucleate and form the solid phase. If you keep cooling down, that so nucleation, then growth of the solid phase, end up having all these solids consume the liquid, transform to solid phase, the alpha. And then once you hit down below this point, if you remember this line, we call this one the solvus line, right? So that means this can tell you how much it can accommodate the other elements, in this case the 10. Huh? So if you cool below this line at this point, now at this point, alpha cannot accommodate more 10, right? So what's going to happen is you're going to have this beta as a particulate, as going to precipitate it. It's going to precipitate it outside of the alpha phase. So you see beta particles plus the alpha phase. Okay. Now the question is, what's going to happen if you have the eutectic composition? So if you have a eutectic composition, we said there's a very special composition, a special point, because at this point, we said that the liquid can directly transform to two solids, اللي هو alpha plus beta. But really what's special about this is the liquid can transform directly to alpha plus beta, but alpha and beta, they have a special microstructure because they're going to have alternating layers to form lamella structure. So you're going to have alpha, beta, alpha, beta, alpha, beta, okay? As you can see here in this image over here. So you have different grains. Each grain has alpha, beta. Now, and then if you look at the macrograph over here, you see that alpha, beta, alpha, beta. So in each grain, you can see that we have those alternating layers, okay? So now, if you have an alloy with this composition 61.9 and you cool down from the liquid phase to solid phase, the liquid can directly transform to solid phase alpha plus beta, and that alpha plus beta has a special microstructure here, lamella structure. Okay, so let's see what's gonna what's happening during the solidification. Okay, so before we get into this, let's remind you of this. Okay, alpha is representing the rich phase of lead. Beta is representing the rich phase of alpha. Beta is representing the rich phase of 10. Ma'am. Okay, so this is the solid phase. And this is the liquid phase. So during the solidification, what's going to happen at the end of the solidification process, the solid will consume the whole liquid, right? So this is representing the interface. So this is representing this is representing the interface between the solid and the liquid. Okay, so at that interface, in the liquid phase, you have tin and lead, and we know that the alpha phase is representing the rich phase of rich phase of lead, and the beta phase is representing the rich phase of tin. This is why in the liquid, the tin will try to diffuse toward the beta phase, right? So it's going to try to diffuse toward the beta phase. Similarly, a lead is going to try to diffuse toward the alpha phase, right? Because alpha can accommodate more lead compared with tin, right? So that's going to result in, so as this interface move into this direction, right, you're going to keep forming this alternating layer of alpha plus beta. Okay. Now the question is, if this is what's happening, if you have a eutectic composition, the question is, what's happening if you have a composition that is below the eutectic composition or higher than the eutectic composition? Okay, let's look at this point. Okay, now if you are below the eutectic composition, so now this is the eutectic composition, 61.9. If you are below the eutectic composition, if you are, let's say you have 48%, right? So, and you have a liquid phase, if you start to cool down, you hit this region, part of the liquid can transform to, part of the liquid can transform to alpha, right? But once you hit this eutectic temperature, we said before, any liquid you have gonna transform to a special type of alpha and beta. وهذا special type عبارة عن alternating layer. حلو? So any liquid you have below the eutectic temperature, it's gonna transform to alternating layer. If you are at the eutectic composition, the whole liquid gonna transform to alternating layer. If you are below the eutectic composition or higher than eutectic composition, the liquid gonna transform to alternating layer, plus you have something else in your microstructure, which is the alpha that's already been formed before you have this temperature. Similarly, if you have composition that is higher than the eutectic composition, you say that the liquid gonna transform to alternating layer, but in addition to that, also you have a special type of beta that already formed before this temperature. We call this a primary beta. Okay. That means if you look at this of the microstructure that we have at this point. Okay, so at this point you have composition that is lower than the eutectic composition. What's going to happen? We said you have how many phases exist? We say that we have alpha and we have beta, but we have two types of alpha. You have primary alpha that's already formed before the eutectic temperature, and you have eutectic alpha that's the result of the liquid transformation as you cool it below the eutectic temperature. معناته this alternating layer is the result of liquid solidification below the eutectic temperature, right? And these regions, sphere regions over here, is the primary alpha that's already formed before the eutectic temperature. I would like to remind you again, liquid gonna transform to lamella structure below the eutectic temperature only between this composition, if you are between this composition and this composition, right? Between 18.3 and 97.8, okay? Because if you are at this point, this will not happen, okay? Okay. Okay. Wonderful. So now let's deal with some numbers. Let's extract some information from here. Okay. Now, if you are at this point, if you are at this point below the eutectic temperature, if you are below the eutectic temperature at this point, you want to know how much alpha you have. Oh, before that, the simple question is, what is the weight, what is the composition of alpha and beta? Because at this point, you know that you have alpha and beta. How much, what is the composition of alpha, what is the composition of beta? We say we're gonna construct a horizontal line, hit the two regions, right? And then you go to the x-axis, y-axis. So here you have 18.3%, 10, and for the beta we have 97.8, 10. Then the following question is, what is the weight fraction of total alpha? Total alpha, regardless whether it's primary alpha or eutectic alpha. Huh? Because you see here you have two types of alpha. You have eutectic alpha and primary alpha. If you want to calculate how much total alpha you have and how much total beta you have, what you're gonna do, you're gonna use the level rule, right? So in the level rule, what you're gonna do is, in the level rule, we're gonna say what is the distance between this point and this region, we call it R. This is between this region and this region, we call it S, right? And then now, if we want to know how much alpha we have, we're gonna say, we're gonna take the distance of the opposite side. You're gonna take the distance of the opposite side, here we call it S, right? So S over the total distance, here R plus S. If you want to know the weight fraction of beta, what you can do, so beta, you're going to take the distance of the opposite side, here R, and then you divide it by R plus S, here total distance. Or you can say, I know that I have two main phases, alpha and beta. So we can say 1 minus 0.73 is going to tell you 0.27. So by using these, by using this level over here, we can know what is the total alpha you have, regardless whether it is primary alpha or eutectic alpha. Okay. Again, also, if you use this rule, اللي هو weight fraction of alpha, using this level rule, you have to know that this total 0.73 weight fraction, it's made of two types of alpha, primary alpha and eutectic alpha. Okay. So you're going to have primary alpha, primary beta if you are below the eutectic composition, and if you are higher than the eutectic composition. If you are below the eutectic composition, we call it hypoeutectic. Hypoeutectic. If you are in a composition that is higher than the eutectic composition, we call it hypereutectic, right? And in both cases, what you can notice that in addition to the lamellar structure that you have additional microstructure here, microconstituent, which is the primary alpha, right? Similarly here, if you have hypereutectic, where you have, in addition to the lamellar structure, you get this primary beta over here. طيب? Only at specific composition, which is the eutectic composition, where the whole liquid kind of transform directly to lamellar structure of alpha plus beta. Okay, so I think I'm almost at the end of this lecture, and I want to point out something, which is now we use this level rule over here اللي هو for weight fraction of alpha and beta. طيب, to calculate the total amount of alpha, total amount of beta, صح? And if we want to calculate how much we have primary alpha, okay, what we will do, we're gonna say if this is your composition 48%, let's also point out the other important region in order to construct the lever rule. This is the eutectic region, 61.9. And this is the alpha region, which is 18.3. If you do the lever rule between this line and this line and this line and this line over here, so you're making the lever rule between the eutectic region and the alpha region. معناته you're trying to, you can find the fraction of the eutectic اللي هو كل اللاملا structure and the fraction of the primary alpha. So if you call this one T, okay, and we call this one M, طيب, if you call this T and M, so if you want to know how much primary alpha you have, we're going to say primary alpha عبارة عن the opposite side اللي هو M over T plus M يعطينا, it's going to give you the primary alpha. If you want to know how much eutectic structure, not eutectic alpha, I'm saying eutectic structure, how much eutectic you have, you're going to say the distance of the opposite side اللي هو T over T plus M. This is going to give you the weight fraction of the eutectic. Okay, so if you go in the book, you're going to find a very good examples that's going to also clarify this point in much better way. It's going to also help you to practice how you can know the weight fraction of each phase. Okay, so I will be stop here, and then we're going to continue in next lecture, inshallah ta'ala, to talk about other important reactions that we might see in the phase diagram. So today we'll learn that there is a special reaction called eutectic reaction, where the liquid is going to transform directly to 2 types of solid. So one liquid, if you cool it down, it's going to transform to 2 types of solid, right? And also these two types of solids, if you melt it, it's going to transform directly to a single type of liquid. In the next lecture, we're going to learn about a new kind of reactions and other type of reaction where you have the solid upon cooling down, it's going to transform to 2 types of solids, or maybe or the 2 solids upon heating up, it's going to transform to a single type of solid. We call this one eutectoid. I'm going to introduce you something called eutectoid. Today we'll learn about eutectic. Next lecture we're going to talk about eutectoid. And eutectoid, I mean, it's kind of similar to what's happening to the eutectic. So and we're going to talk more in detail, inshallah ta'ala, in the next lecture.